Hello, and welcome back to Beyond Networks, the Evolution of Living Systems. In this module, we're going to dive into the theory of dynamical systems, and we're going to introduce its basic methods and its basic concepts that you can use as conceptual tools to understand the dynamics of a process. In the next module, we're going to connect that back to the fact that we use these formal models, dynamical systems model, to study underlying processes and to discover the causal structure that produce the patterns that we observe in nature. But here, for the next 4 lectures, we're going to sort of play around with formal models as epistemic tools. Remember that? And I'm going to introduce a bunch of concepts and approaches that are helpful to address this specific question. What does a process do? How is a phenomenon that we see in development produced? What is its mechanism? I start this lecture in a slightly unusual way. First of all, I have to confess that I stole most of it from my longtime mathematical collaborator, Nick Monk, who is giving this brilliant introduction to dynamical systems theory. And I couldn't improve much on it, so I've just adopted it. I'm sure Nick doesn't mind. And also, I want to have a quick advertisement section here because there is a book. There's a book you should know about. And this book has a very dry title. It's called Nonlinear Dynamics and Chaos. It's written by Steven Strogatz, an absolutely exceptional mathematician. And I cannot recommend this book highly enough. Even if you have been on a warpath against mathematics so far. This book takes a uniquely sort of visual, geometrical approach to teach you the concepts of dynamical systems theory. It is a brilliant, pedagogical sort of piece of very gentle introduction into dynamical systems theory. It is a masterpiece. So if you want to know more about the mathematics and the technical details of what I'm telling you here, please consult this book. It's absolutely brilliant. So let's just recap very briefly where we left off. I was telling you about actual systems being pattern processes in nature, and that we wanted to have some sort of formal modeling approach, a formal perspective on those processes to get a mechanistic explanation. So we want to understand how these processes look like in a causal manner. So we want to know what is causing what. And the basic sort of task, to use Waddington's epigenetic landscape metaphor, is to understand the shape, the geometry of what Waddington called a creode, what we nowadays call a developmental trajectory. If we understand this shape, we understand what the system does. So the underlying sort of system is very complicated. And so I would sort of like to shift the focus from the pattern that we observe to sort of the set of rules or the structure of the process underneath. I was telling you before that at the moment, the way we describe these structures is using these network graphs. We're using network analysis to understand what's going on. But I hope to have convinced you that these networks are idealized representations of pattern processes. And very important, network graphs don't tell us what the network does, okay? So therefore, they do not provide mechanistic explanations in themselves. They pose a challenge to understand what they do, but they don't provide a solution. Mechanistic explanations require us not only to decompose a system into its components and their interactions, like we do when we draw the graph. We compose a parts list, and then the graph is drawn out of the interactions between the parts. But we also have to recompose it to understand the organized activities, how all of those activities and interactions work together to produce the phenomenon the mechanism is supposed to explain. So counterintuitively, giving a mechanistic explanation, especially in development, is not just to take a developmental system apart, but also to put it together again, to not only identify those components that are necessary, but also show that the interactions and the components that we have are sufficient to explain the phenomenon that we're studying. Recomposition and that's how I ended the last lecture, requires a dynamical system model of the system. So basically, you need a computational or a mathematical model to track all those different interactions in the complex network, because of all the sheer number of interactions, their nonlinearity, unpredictability, and the lots of feedbacks that occur in the system. This is where we left off last time. And so to summarize that, once again, is we're trying to understand an actual system, which is a patterned process in nature with a formal system, a set of relations between mathematical objects, variables in the case of dynamical systems that are described by equations. We'll get to that. And we bring those two into congruence by the activity of modeling. Again, I'm looking at modeling and models as some sort of tools for understanding. So dynamical systems models are tools for understanding the behavior or the dynamics of a developmental process. So what are dynamical systems? An important thing here is that we don't need to start with the mathematics or some sort of mathematical definition, because dynamical systems are formal descriptions of the structured processes that happen in reality. They are defined by a well-defined state. Okay, so a system has a specific state. The states, there's one state after the other, and there is a set of rules, which we call the structure of the system, that describes how you get from one state to the other. So that set of rules determines the succession of states over time. Those are all the ingredients you need for a dynamical systems model. How you formalize it mathematically can differ. We'll get to that at the end of the lecture. But those are the basic ingredients. Examples of states could be, classically, position and velocity of a moving point particle in space. We'll get back to that in a minute. But historically, this is how dynamical systems theory started, by creating models of the movement of objects, planets, and moons in the solar system in space. But the state of dynamical systems could also be concentrations of metabolites or mRNA and or protein in a cell, or even in a multicellular aggregate, a tissue. So these are gene regulatory network models or metabolic models. Or obviously you could study, using dynamical systems theory, allele frequencies in a population. So population genetics uses dynamical systems as well, sometimes in beautiful ways, by the way. So a very central and important concept is that a dynamical system is what a dynamical system does, okay? We do not need any mathematical formalism to characterize the dynamics of a system, because we can observe the dynamics. What the system does can be investigated empirically. We can see it, we can measure it. I'll give you an example in a minute. And the mathematics come in where we deal with how to represent the resulting data in a useful and efficient form. Okay, so mathematics, again, tools for thinking, but only as an afterthought. Okay, so dynamical systems are nothing abstract in that sense. We can observe the behavior we want to describe, then we formalize it. So we're going to take this approach and sort of look at a dynamical system that I've already introduced when we talked about actual versus formal systems. And that is the linear pendulum, Galileo's pendulum. Okay, so a pendulum as a physical system, just to repeat that quickly, is a rod, cord, wire, etc., with a weight or a bob at the end, at one end. It's suspended from a fixed point so as to swing or oscillate freely under the influence of gravity. So you have here a rod, in this case in the idealized model, it's a stiff rod and a bob. At the end it has a certain weight and it swings around at a certain angle around its equilibrium position here in the middle, under the influence of the Earth's gravitational field. And this already shows us one thing. There's a split in the world here. We've separated the system and the environment, the pendulum and the Earth. A pendulum on the moon on a spaceship is going to work differently than a pendulum on Earth. So this separation, always remember, is always relative to context. Okay? It's a part of formalizing the system. So let's explore the dynamical repertoire of this pendulum in an empirical way, as I said. So we have a swinging pendulum, and empirically, we can represent the state of the pendulum. The first thing we need to think about is, what is the state of the system? It has two variables in this particular case, the position and the velocity of the ball. Those are the variables because they are the quantities that vary as the pendulum swings. We can then explore the set of its dynamical behaviors, which is called its dynamical repertoire. Remember that term. By setting different initial conditions for these two variables and by plotting position and velocity as a time series. So you pull the ball up different directions to different heights, and then you let it swing, and then you measure it. Okay, so that's what we've done here, and that's what I've graphed in this time series. So in this graph, time proceeds to the right, and the magnitude, so the amplitude of the oscillation is plotted here as these yellow lines of position. This means, let's get a bit more concrete. If you're on this side, you are in negative space left of the equilibrium position. And your velocity here, the red line, is 0. You stopped at the extreme point of the swing. When you're in the middle at the equilibrium position, your position has gone to 0. We've arbitrarily set that position to 0, and your velocity is maximal. Okay, so you've accelerated downwards, and now you're going upwards again. So you're slowing down, velocity is going down, position is going up because you're moving to the right. So now you're here, and then you swing back. So after half a period of the oscillation, you're back at the equilibrium position until you finally end up at the place where you started. And so what you get is a sort of a representation of the system's behavior in time. And you can see the two state variables, they oscillate out of phase from each other. Now, you can use a certain trick to make this simpler, okay? We can characterize dynamical behavior in a more compact way by plotting the position and velocity on the phase space of the system. The phase space is defined by the two variables. So the two axes in this graph now are velocity on the y-axis and position on the x-axis. And because we have two variables, the phase space of this system is two-dimensional. It's called a phase plane. Okay? So if we plot the behavior of the pendulum in this abstract space, the phase space of the system, you can see that it circles around the center here. Okay? And the radius of the circle depends on how far you pulled the pendulum out when you started it. Very simple. Okay? This is called a trajectory of the system. Remember, this is all just observation and plotting. There's no mathematics involved here. Okay, we can then collect the dynamical behaviors for all possible initial conditions to complete what we call the phase portrait of the system. So if we draw all the possible trajectories, then we get, in the phase plane, we get the phase portrait of the system. So I'm showing the original trajectory here in the middle, and there's all kinds of other trajectories. This is a smaller pendulum. There's a position. When you start the pendulum from all the way on the top, then it'll, if there's no friction, it'll go to the top, it'll swing back, okay? So that's a very special trajectory, this one here. And then if you push it from that position, it'll start going around, okay? So it'll start swinging, and that's represented by these oscillatory waves out here. So there are different, qualitatively different types of behavior, and they are represented by qualitatively different geometries of the trajectories in the phase space. You can learn a lot from that. So each point on this phase space represents an instantaneous state of the system. And we said a dynamical system is just a succession of different states. This is why the phase plane is also called the state space of the system. Okay, phase space, state space, is the same thing. So in this case, the phase space, the behavior is periodic. So we don't need to draw it out endlessly on either side. So if we draw it from minus 2 pi to plus 2 pi, that's covering the whole circle. That's covering the entire behavior. And then we just have, outside of this, we have a repetition of the same behavior. So this image here is the total of possible behaviors of the system. And so what we can do is, because this repeats outside here, we can do this sort of toilet roll trick. We can roll up the state space, the phase space, on a cylinder and depict it this way. It's a very compact way. And so this sort of cylindrical phase portrait of the system, if we have that, if we understand that, we understand all the behaviors the system has. We understand completely what the system can do. Okay, and this is how dynamical systems models are useful as a tool to get explanations of what a system can do. Okay, so we've collected all the different behaviors, we've drawn the phase portrait, and just to repeat that, as a dynamical system, rather than an artifact, rather than the actual physical system, this is the formal system we're talking about here. The pendulum is what it does, not what it is made of. So basically, this phase portrait is a representation of the system. It is no different from the system. Its entire dynamical repertoire is captured in the phase portrait. So there are a bunch of features that are really interesting in this phase portrait. The first, and this is highly unusual actually, in this system, we have fixed points here, different ones. Fixed points are those states of the system at which its state does not change. If the system is at a specific fixed point, if you don't perturb it, it will stay there. Okay, very simply. And there are different kinds of fixed points. In this case of the pendulum, we have two different fixed points in the phase portrait of the system. We have centers here. They correspond to the pendulum being at the bottom, its equilibrium position. And so it's a sort of at the lowest point of its trajectory. But there's another fixed point, saddle point, which is at the top. Okay, if you put it right there, you have a rigid rod. You have no perturbations, no noise. It's going to stay there. But of course, the behavior of the system is very different. If you push it off the top, it's going to swing very widely. While if you push it off at the bottom, it's just going to keep on being in the neighborhood. It's going to swing around the neighborhood here and not go out further. So there's clear differences, qualitative, between those different points. So another important thing to notice is that change is the norm. So there are very few spots, very few points in the phase portrait that are fixed points. And so mostly the system is in motion. Okay, let's then look at a bunch of other features of the phase portrait. The phase portrait, as I told you already, contains all the potential dynamical behavior, the dynamical repertoire of the system. And every instantiation of the system, every specific experiment we've done with certain initial conditions, we've pulled out the rod just far enough, is represented by a specific trajectory in phase space, for example, this one here. Okay, now the flow of the system, and this is very important, is the sum total of all trajectories in the phase portrait of the system. A dynamical system is its flow. Okay, flow, go with the flow. Flow is very important. Dynamical systems are their flow. If you know about the flow, you know what the system can do, you understand the system. Okay, so how do we formalize the flow? The flow is what we need to know about, right? So let's think about it this way. Through every non-fixed point in the phase portrait, there is only one trajectory, a unique trajectory, a directed curve representing the order of succession of states. Okay, if we have the trajectory, we know how the state changes over time. And we can do some geometry, and we can use some mathematics and describe these curves. In particular, a curve like this has the mathematical form phi, which depends on where the bob is and when, the system is in what state, and it sums up to 0. This is very abstract. Okay, don't worry about it too much, but I can give you a specific example. For a circle like this, we can describe a curve like this with this simple geometrical formula. Okay, this is the formula for a circle on this specific plane. X squared plus y squared equals the radius squared. Okay? So this equation describes a circle of a specific radius r. This is a constant. These two are the variables, remember. So if you set r to different values, you get different circles. This description, though, does not describe these sort of oscillatory waves or this sort of I-shaped saddle point trajectory up here, okay? And there is no reference to time. I said, oh, time is important. You know, we are looking at diachronic biology, extension in time, but there's no time in here. We've abstracted time away. So we can reintroduce time by describing positions on the circle like this, a bit more sophisticated, a bit more involved with the mathematics. But this set of equations gives you the position of the bob in time swinging in a certain direction here, okay? So this corresponds to a clockwise traversal of the circle with angular velocity with a specific speed. Okay, we're going this way. And this is what these arrows mean here. So now if you have an equation like this, for every trajectory, you have a description of the phase space. But this, of course, okay, so the speed at which you move along those trajectories depends on parameters of the system. So it depends on the mass and of the bob and the length of the rod. And so the mass of the bob and the length of the rod will change the behavior, the shape, the specific speed at which the bob transverses these trajectories, but it will not change the generic the layout of this phase. Okay, so this is descriptive, okay, and it's very cumbersome. There are infinitely many trajectories, and you would have to have a system of infinitely many equations to describe them. So that's not what we do. So the trick is that we can identify the velocity with the instantaneous rate of change in position. So the velocity becomes, so here's the angular speed again, and it depends on the change in position, which is represented in Newton's notation here with an x and a dot on top. So this is the derivative. The change in position is the velocity is the derivative of the position. Okay, and so you go from a mathematical form that looks like this, that determines one trajectory in phase space, to a form like this, where the equation no longer depends on an x and a y that are independent, but an x and a derivative of x that are now connected to each other. So the change depends on where you are, basically. Okay, they're connected to each other. And so this simple trick, this simple discovery, is at the heart of differential calculus. It's the invention of the differential equation, an equation that tells you how a system changes over time. And of course, the two people who pioneered it were Gottfried Wilhelm Leibniz, who actually invented differential calculus, and Isaac Newton, who strategically, very smartly copied it, used his own notation, and claimed to have invented it himself. Okay, Leibniz again, process philosopher, big thinker, perspectivist, and the inventor of differential calculus. Very big hero of mine. Okay, so what's happened here? This is a bit abstract. It's a bit mind-boggling, no? Okay, so differential equations. This equation, let me give you an example in a minute. This equation is at the heart of dynamical systems theory. And this formalism allows us to generate trajectories from configurations of the system. Okay, so configurations are particular combinations of system states, where the bob is, how fast it's moving, and the parameters. So how heavy is it and how long is the rod? So all of this together is called a configuration of the system. If we have that, and we have this formalism that you don't have to understand in technical details, you don't have to be able to derive it mathematically, you just have to know that if you have a differential equation, you can automatically generate the entire phase portrait of the system. This is fantastic. So let's see how you get from this general idea and this mathematical characterization of the flow of a system, the dynamical system is its flow, to a mechanism. So in the case of the pendulum, Galileo came and said, you know, just based on observations, he did just what we did right now. So we've basically repeated Galileo's work here. He said, there is a regularity in this system. It's a bit more complicated than what I just told you, because so the position, so the acceleration, the second derivative here, there are two dots. The acceleration of the bob depends inversely on its angular speed squared and the position it's at. So the further away it's from the equilibrium position, the less fast it'll accelerate. And when it's down at the equilibrium position, it'll be accelerating fastest. Okay? It's fastest at the bottom. This sort of equation is just based on observation. It's a differential equation. And Newton identified the second derivative of position with the notion of force. Okay? So in this case, he could then sort of relate the module, Galileo's module of the pendulum, with his own general theory of gravity. So basically, he could relate the pendulum's behavior to the gravitational field of the Earth. That's a sort of a classical covering law sort of explanation. It fits into the general law of gravitation. So from a specified configuration, the specific conditions that we were talking about when I talked about the deductive nomological model of explanation, it is now possible to deduce the forces acting on the system according to the laws of nature, the laws of gravity. And you can construct a differential equation model of the flow. It's a very powerful tool. And you can see now where this idea of Hempel's came from, that that's how science works, because classical mechanics works exactly the way that he describes. So we have this is the system of the pendulum, okay? You have on the left here, beautiful depiction of how the mass of the bob and the gravitational force, they are constant. And so here are the vectors of the velocity and the acceleration, how they change over time as the system oscillates. So you will ask now, if you've been paying attention, what comes first, the state or the flow? Okay, so this formalism doesn't tell you anything about, I told you dynamical systems are their flow. What does that mean, right? So we want to ask this question. So take this differential equation again. It appears in this formalism that if we take a differential equation of this form, the flow is derived from a configuration of the system at a specific time point, okay? Defined at an instantaneous position in space and time. Okay, so if we adopt the process perspective, we focus on the flow. But this flow is secondary. It's derived from states, from configurations, which are things, okay? Horror. I've been talking about how we want to take a process perspective, but now we seem to have taken an approach which is based on a formalism, based on things. But not so fast. Let us think a bit more about where this idea of an instantaneous state comes from. So an instantaneous rate of change, what does that mean? What is this derivative? I just played this magic trick on you before and said, okay, we can now show that velocity is somehow dependent on the position. And we put a dot on the position and it became velocity as the derivative of the position. What does that mean? Okay, so an instantaneous rate of change is basically an abstraction. What we do is we look at change over a specific time interval, okay? And we make this time interval smaller and smaller and smaller. And by the time this interval is infinitely small, that's when we have the instantaneous rate of change, okay? After we've measured change over a specific interval, we make it smaller, 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 it disappears. And the moment it disappears, we have an instantaneous rate of change. Okay, so there is an infinitesimal limit here. The limit for the case that the interval over which we measure change goes to 0. And of course, that's impossible to do in practice. Okay, you need to use mathematical tricks to calculate this instantaneous rate of change. So the idea of an instantaneous moment is an abstraction. Moments, instantaneous moments don't exist. I have a paper where I will, when we finally publish this, argue this. And also on my YouTube channel, there's a talk about the nature of time and the nature of change. I can't go into this right here, but it's important to know that what is fundamental is change. And this idea of these instantaneous states that follow each other, that's an abstraction that help us think about dynamical systems. So you always need finite time intervals to determine the instantaneous rate of change. So instantaneous rates of change are an abstract idealization that presuppose the notion of change and therefore flow. Flow is fundamental. Flow is all there is. The whole universe is flow. Isn't that beautiful? Go with the flow. Everything changes all the time. And things and objects are just sort of stable islands within that flow. So the notion of a dynamical system is founded not on instantaneous states, but on the function phi, which defines the flow of a state space. You don't need to understand the formalism here, but you just need to take this home. The dynamical system is its flow. Phi represents the flow, represents the dynamic structure of the system, the topology of the phase space, which determines the repertoire of potential dynamical behaviors, the dynamical repertoire of the system. So we can use a lot of different mathematical formalisms. This is how I end this lecture, just by quickly letting you know that you could have systems that have a continuous time flow and continuous variables, for example, concentrations that are changing continuously over time. Or you could have a dynamical system that goes stepwise. The time is discretized. There are time steps. And also it could be that the qualities, for example, you can have a logical model of a gene network where the genes just switch on off instantaneously. There's no continuous sort of concentration. There are different mathematical formalisms to describe this. Also depending on whether you include noise or not in your system. So if you have a continuous time, continuous concentration system and noise, you get stochastic differential equations. So there are lots of formalisms for that. Chemical master equation, Langevin equations are used by biochemists, for example, to describe chemists and biochemists to describe chemical reactions. Or, and we're going to focus on this here, you could have a deterministic system of differential equations without any noise. So we're just going to, for now, we're going to abstract away from the noise. Iterated maps, discrete systems, you can formalize using Markov models where each step in the model depends by a certain probability on the last step. And also Markov models can have variable memories. So a Markov chain has just a memory of 1, okay? Everything, the next step always just depends on the current state. But it's possible to have systems with memory. We'll come back to that also. And you can have Boolean logical models with discrete time, discrete sort of variables, and discrete maps with continuous states. For example, famous from ecology is the logistical map. You don't have to worry about these. I'm just saying there's many different ways to describe a dynamical system, but the underlying principles, the flow, as I have introduced it here, the trajectories of the system, they don't depend on the math. Basically, the mathematics are just a way of dealing with the system. They are not what defines the system. So, I'm sorry, this was very technical, but, and you probably think, I haven't signed up for a physics course here, but we've introduced a number of really interesting concepts. The dynamical system is its flow. The flow is made of all these trajectories. We've used the pendulum to introduce these, and we're going to use in the next lecture, we're going to apply those concepts to a very, very simple system of a gene regulatory network. I hope I haven't scared you off, and you will tune in again for that. In the meantime, thanks for listening, and see you next time.